Hi, and thanks for joining us. I'm Andreas Spitz, and together with Dennis Aumiller, I'd like to give you an overview over our hypergraph model for large document collections. Now, as a model, it is abstract, so let's start with a concrete example instead. This is a scene from the movie Dark Waters, in which an environmental attorney is going up against a chemical company that is poisoning the local water supply. And when he subpoenas them for their information, they simply send him all the documents they have in an attempt to drown out the useful information. So now he's faced with this intense information overload, where he has a lot of heterogeneous documents in which he has to find the bits of information that are actually useful to him, and he probably doesn't understand all of the documents because there's chemical language in them. Now, obviously, this is not a completely new problem, and we've probably all faced this at some point in the past. And there are a lot of different approaches that could be useful here, right? You could search the documents, extract entity relations, build knowledge bases, detect events, use topic modeling or summarization, and so on. In each of those approaches typically come with their own model for representing the data that enables this solution. So from the very old and established bag of words and vector space models, all the way to the new neural language models. And the commonalities between those models is that we always look at co-occurrences between entities or words and just things that occur together because the context gives us the information that we are interested in. But what is missing is a versatile and unified model where you have one model that supports most of the approaches on the left, right? And not one individual model for each of the approaches. And the reason why this does not exist yet is that it's quite challenging and a lot of work to come up with a good model that stands to support most of these tasks. And some of these challenges are that you have to integrate structured and unstructured data, right? So if you have entity annotations in your document, you might want to link them to an external knowledge base so that you have more information about those entities. You also need to account for very flexible co-occurrence window sizes, because if you have an approach like n-grams, you only need to look at like the next 4 or 5 words. But if you have something like summarization, you want to work on the sentence level. So your co-occurrence windows are much larger, and the unified model needs to be able to account for all of these. And finally, while there are a lot of graph-based approaches, you need to capture higher order co-occurrences. So the typical dyadic co-occurrences of 2 words or entities are not sufficient if you want to have multiple people at the same space or multiple chemical reagents that interact. So you need to have higher order co-occurrences up to an arbitrary level. And the versatile model needs to capture all of those. And this is kind of what leads us to the motivation for a hypergraph document model, where so let's assume, to construct the data representation, that we have a document D, which has sentences R, S, and T, and then each of those sentences contain words or phrases or however you want to split up the components of the sentences. And then the idea is that for each of the sentences, so here as an example, let's focus on the sentence S, we have an hyperedge that represents not just this sentence, but also the surrounding sentences, right? So here it's just one surrounding sentence, but the windows can be arbitrarily large. And instead of just putting in the contents of the sentences, we also put in the structural elements. So what we then get is a hyperedge in which each node represents the document, a sentence, or one of the components of the sentences. And they each have 2 components. So one is an identifier for this word or phrase or sentence or document, and one is the distance to the core sentence. And then ideally, each sentence is represented by one such hyperedge. Now this sounds like it's going to lead to a lot of data replication, and then practice is it does not, but I will get back to this later on. And obviously this solves the problem of having higher order co-occurrences and arbitrary co-occurrence window sizes, because we can model this. It also solves the problem of integrating external data sources, because we have the position and the core, as I just mentioned, but we can also have additional attributes, right? So we could identify the part of speech of a component or the timestamp of a document. We could have external knowledge base IDs for entities in the text. And this is the data representation that we're going to use in the following. This is a bit simplified. The details are in the paper if you're interested. Now, to get information from this, we introduce 4 very basic operators that you can use to just select what you need or what kind of co-occurrences you need. And the first one is a selection, where, so assuming we have 2 hyperedges as input on the left with the yellow and the purple vertices, so nodes in them, and then we just want to select edges that have nodes that meet certain criteria here. So here is just select purple nodes, but this could be an arbitrary expression that you can use here. Similarly, we can have a projection operation that removes nodes from hyperedges that we're not interested in. So if we say project to the yellow nodes, then the purple nodes are removed. And again, this can be an arbitrary propositional expression. We can also reduce the hyperedges back to dyadic, so normal graph edges, to support approaches that don't need the higher order co-occurrence information. And finally, we can introduce the operator of a join. So let's assume that we have 2 different sets of hyperedges. So this is E in one set and then F and G in the other set. And we can join them to create larger hyperedges. So here we would join on the X and Z node. And so to give you a bit more of an understanding of how this would work in practice, we can then chain those operators to get the co-occurrence information. So let's assume that we have some document collection that is represented by a set of hyperedges E, and we want to find mentions of persons you and me. So what we can then do is we take the entire set, we select only edges in which you are mentioned, and from this we select only edges in which I am mentioned, and then we can project this down to the type of sentence to give us the sentence identified. Right? So you can see that we are actually just chaining the different operators to get the set of nodes that we are interested in. And obviously, this doesn't have to be sentence nodes. We could also project it to the set of words if we then want to continue with those words, right? So this is just a very simple example. And in the paper, we go through how this can be used to map to very established IR approaches. Now, one thing that you might have noticed is that this is very similar to relational algebra, right? So if we just say that hyperedges kind of relate to tuples in a table, then the hypergraph operators, projection, selection, and join, they're very similar to the relational algebra operators of projection, selection, and join. And this is by design, right? So we want to have a very simple set, and we also want to be able to represent this data ideally in a relational database management system, so we can just use it on top. And Dennis will talk about this afterwards. Now, one question you might have is, how feasible is this actually? And so hypergraphs are well known to be a computational nightmare because of the complexity, especially if you look at multi-hop distances between nodes. But here, the structure of natural language comes to the rescue, because natural language sentences are not arbitrarily long. So we don't get very large hyperedges, and we stay within a manageable regime. So this is kind of very similar to the idea of how a bounded tree width in a graph gives you computational feasibility even for NP-hard problems. And here we have something similar where the size of hyperedges gives us feasibility in actually working with them. The second problem might be storage space requirements, where you obviously have a lot of potential replication if you explicitly store the contexts of each sentence multiple times. And here the general insight is that we don't necessarily have to do this. So sentences can be stored sequentially in memory, and then we can generate the hyper edges implicitly at create time. And this is what we're going to see in the following. So now I'll hand over to Dennis, who will talk a bit about the implementation and evaluation.
Thank you, Andreas. Starting with the evaluation setup, we will look at the various dimensions which are relevant for this talk. Specifically, we look at the materialization of hyperedges and whether they should be pre-computed as an explicit model or computed at the runtime in an implicit model. Dyadic representations are an obvious choice as a baseline here. Coming to the systems, we start looking both at Postgres as a representative of the relational database family and similarly Neo4j as a representative of the graph database family. For datasets, it might be useful to have the full dataset available, but in some use cases, like news articles, it is sufficient to limit oneself to the main focus of entities, namely persons, locations, and dates in the text. Our dataset does in fact constitute of around 113,000 previously collected English news articles, which come from heterogeneous sources, making them an ideal candidate for evaluation. In all, they have around 400,000 terms, a third of which is restricted to named entities, and they already come pre-computed and split as we need them for our evaluation setup. Looking at Postgres, we see that we do need the document representation for all of the models as an underlying storage. However, only explicit models require the additional modeling of hyperedges in separate representations. Similarly, Neo4j has a setup but requires the explicit modeling of hyperedges due to it being limited to dyadic representations between nodes internally. However, we can still model the remaining part of the document and specifically its hierarchical components in a similar fashion. The occurrences are then simply modeled as relationships between different nodes. Looking at the storage space, we can make several observations, the most obvious being that we do have in fact a linear growth in the number of documents. The only difference between different model implementations is the factor by which they grow. However, looking at various window context sizes, which we model in the figure on the right, we do make some more interesting observations, and specifically starting with the constant factor for the implicit model. As we do not have any additional overhead for the storage of hypergraphs, this is by far the most storage efficient model. Dyadic models, on the other hand, are quite expensive to store, specifically due to the increase in edges from the reduction operation. Comparing, for example, the explicit entity model with the dyadic entity model, we can see that this is quite a huge factor of more overhead. We didn't even manage to actually process the dyadic representation of the full graph, which is left out in this figure. Comparing the evaluation of entity-reduced and full dataset models, in this case for the hypergraphs, we can still see that there is quite a significant factor. Keeping in mind that this is a log scale, we're talking about a factor of 10 less of storage space. Generally, we also see that Neo4j tends to be more efficient for node-heavy representations, those is specifically hypergraphs, since they have a somewhat cheaper overhead internally. However, once we start gaining more edges, for example, in the dyadic representations, Neo4j tends to be a little more expensive. So overall, we are somewhat on par depending on the explicit context window size and model used. Hyperedges, however, tend to be quite efficient for the large context windows because they do not have any additional overhead past a certain window size, whereas the window size does introduce, especially for dyadic models, a larger context. Coming to the query performance, we are also posed with several new challenges, specifically how we treat the internal optimizer of both Postgres and Neo4j. We mostly treat them as a black box because there is really no way to fix both the models, especially when coupling this with the problem of caching, for which we actually give the systems the chances to catch up by having one pre-cache warm-up run and then evaluating the quickness of the query performance. Lastly, the query complexity itself plays a big role as well. We alleviate this by having only a very simple case where we evaluate how often does a specific term co-occur with our query term X. This is very controllable and yields a relatively simple internally optimized tree, which we can then use to evaluate somewhat consistently across models. Of course, there is no time to really look at all the different models, but we do give a brief highlight session on the right here. Keep in mind that these are the model's explicit entity implemented in Postgres, the one exception being figure D, which is the Neo4j equivalent. Starting by the comparison of, again, the explicit and dyadic representation, we say that the explicit entity models tend to perform quite well, especially on the larger context. However, dyadic representations are still somewhat convenient for especially small window sizes where they have a similar performance on like a sub 100 millisecond scale. Complementing this with a comparison between explicit and implicit representations, it shows that while the implicit model is somewhat more expensive, it is still competitive, and especially for larger contexts, maintains a relatively constant factor of slower queries, but doesn't grow exponentially as we might expect. Comparing Postgres with Neo4j, this is maybe one of the exceptions where we see where Neo4j struggles a bit with what we expect as caching issues. However, on general notes, the two models do perform more or less on par, but generally Postgres seems to have a slight advantage in some models, for example, the ones with larger context windows, where caching is quite beneficial. To wrap up, in this talk, we have introduced a model for representation and querying of large annotated data collections as heterogeneous hypergraphs. Specifically, we've also formalized a set of IR operators on top of this model, which supports a wide range of tasks. During our evaluation, it has been shown that relational databases are actually on par with graph-based solutions, which is interesting for future work. Since currently there is no fixed one-size-fits-all approach, at least in existing systems, we also may be interested to look into a more native implementation of said query operators. Currently, those are implemented SQL, but this can be obviously extended to the low-level code of several systems. And already during our evaluation, we have shown that there is quite a problem with larger contexts and thus the scalability of both systems, which also asks for a better look at the potential of distributed storage solutions. With that, we want to point interested listeners to our full publication and the code that we have publicly available for the evaluation setup. And thank you for your attention. To answer any questions, you can find us in the Slack channel and ask ahead.